Welcome to the pilot of our new show, springboarding off of the molecular show, which was unfortunately cancelled. In this episode, we'll be covering the mechanism of radical halogenation with methane and a bromine, and then generalize the reaction to a more complex alkane. The reaction is split into three steps, the first being initiation. We'll begin with the halogen bromine. Using heat or light, the bromine bond can be split and one electron goes to each bromine, forming two separate radicals. We represent the movement of a single electron with a one-sided arrow. We only need to form a small amount of radicals, and we'll see why in the next step. The second step, propagation, is where the meat of the reaction happens and where the major product is formed. The Br radical takes one of the electrons from the CH bond and forms a CH3 radical and HBr. This CH3 radical then goes to react with a Br2 molecule, forming our major product, CH3Br, and a Br radical. This radical can then go react with more methane and the reaction cycles, hence the name propagation. This is why we don't need to form too many radicals in initiation, because one radical has the potential to react thousands of times. Also, if there's an excess of the halogen and its radicals, often more hydrogens can be switched out for the halogen. The last step, termination, actually isn't the last step of the reaction. It's always happening throughout the other steps. Termination is when any two radicals come together to form a more stable molecule. This could be two Br radicals, which is the reverse of initiation, two CH3 radicals, which forms a minor side product, or a CH3 and a Br radical. This last one actually forms our major product, however it's in a very small amount. Less than 1% of the product is formed through termination. On a side note, a radical is flat, so the other reactants come in either from the top or the bottom. Therefore, the reaction is neither stereoselective or specific, it's racemic. A radical can be stabilized much like how a carbocation is stabilized. The more substituted the radical, the more stable it is. When a more complex compound, such as methylpropane, reacts, there are more hydrogens that the halogen can replace. The major product that forms is greatly influenced by radical stability. Statistically, due to the number of primary hydrogens to tertiary hydrogens, 90% of the product should have the Br attached to a primary carbon and 10% to the tertiary carbon. But due to the tertiary radical being more stable, 99.4% of the product has the Br attached to the tertiary and only 0.6% is bonded to the primary. Hopefully this helps develop a better understanding of the mechanism for radical halogenation and regioselectivity due to radical stability. Thank you for watching, and we hope to see you again.